Hello everyone and welcome to another college algebra video. In this video I will talk more about log properties, more specifically log properties that you haven't seen yet. We will be talking about condensing and expanding logs, and we will also talk about the change of base. The change of base formula. And really what this means is how to make sense of uncommon logs. And just so you're aware, that's any log that is not log base 10 or natural log. So any other log other than that, log base 2, log base 7, log base 1.09. Again, we can have any base we like as long as it's not equal to 1 and it's a positive number. I'll get more into it. Let's look at expanding and condensing logs. Before we get into expanding and condensing logs, I need to first explain these properties. So here we have log base b of m times n. So let me mark this with a different color. When you have two expressions being multiplied, or in fact we can say two different bases being multiplied, we can expand a log out into log base b of m plus log base b of n. And we can do something very similar over here with the division. We have log base b of m over n in the second property here. And as you'll notice, I highlighted this in blue. That's because we will take the log of the top base and subtract the log of the bottom base. And for the last one here, property number 3, we have log base b of m to the p power. What we can do with that p is we can move it to the front of the log. So what that means is we can take the exponent and we can move it, the power, to the front of the log. We can turn it into a coefficient. So these properties have names. We have the product rule, because that's what happens. This is the rule how we can expand if two bases are being multiplied. We have the quotient rule, which is how we can expand if two bases are being divided. And we have the power rule, which is what we can do if we have a power on any of our bases. Now, one more thing before we go in here is we can expand. So let me see, expand. And that means we will start on the left side of any of these equations. So if we see two bases being multiplied or two bases being divided, or a base with an exponent, we can expand it out by doing these rules in this way. We turn the left side into the right side. But pretty soon we are going to also be condensing. And that means we need to start here on the right side. Condensing, we start here and turn 2 logs into 1, or we turn 2 logs into 1, or we put that coefficient back into the exponent. And in fact, we can condense multiple logs. We can condense 15 logs if we needed to. And for this course, for college algebra, for algebra 2, it's much more useful to know how to condense. Expanding will make much more sense and be much more useful in later courses, later math courses. But yeah, so condensing is where the focus will be, but since we are doing condensing, we will also learn how to expand. Let's take a look at expansion and get that out of the way. All right, expand and simplify. These are the directions that we will use for every single example until we get to condensing. So what we will have to do first is simplify the argument, and that's if we can. Sometimes, probably all the times, at least in college algebra, we don't need to simplify the argument before we start expanding. Then, step 2, we can expand the log using the product and quotient rules. So we have to start with product and quotient rules as we expand. Step 3, after we expand using the product and quotient rules, we can get to expanding the log using the power rule. And from there, we can simplify logs if it's possible. So if we get at the end of our expansion and we can simplify a log, we should do that. All right, let's take a look at number 1. And I like starting with examples like number 1 and number 2 here because students really quickly lose sight of the fact that there are two things being multiplied here. This 9 is being multiplied to the x. So we can actually expand this out into 2 logs. Can we simplify anything in this argument first? No. So let's expand using the product and quotient rule. Since we have a 9 being multiplied by an x, those are 2 different bases, which means we can have 2 different logs. Log base 9 of 9 plus log base 9 of x. Cool. All right. Well, we can then expand using the power rule. Well, I don't see any exponents here on the 9 or the x, so we don't have a power rule yet. And then, if possible, simplify these logs. Well, log base 9 of x, normally, if a base is numeric and the argument has a variable, we won't be simplifying this. However, if both the base and the argument are numeric, then we will have to simplify it if it can be simplified still. So remember, a log is just asking what exponent. What exponent do I need to make 9 into a 9? Well, it's just going to be exponent 1. So this log simplifies to 1. We have plus log base 9 of x. All right, first expansion, done. Next, we have log base 2 of 32 over x. And again, this has 2 bases. It's just 1 base is in the numerator and 1 base is in the denominator. So we can use the quotient rule here. That's what a division is. It's a quotient. We can separate these into their own logs, log base 2 of 32 and log base 2 of x. Now here's the awesome thing about expanding these logs. Any base that comes out of the numerator will be a positive log. Any base that comes out of the denominator will be a negative log. Cool, so there you go, you've got it. Let's see, expand using product and quotient. Yep, we couldn't simplify this fraction at all. We didn't have to do this. Expand using quotient and product. Yep, we used the quotient rule. Expand logs using the power rule, the 32 or x, neither of them have a power. And then if possible, simplify logs. Again, a numeric base with a variable argument can't be simplified, but we have a numeric base and a numeric argument. We gotta check. All right, what power of 2 gives me 32? Can you think of one? It's gonna be 5. 2 to the 5th power equals 32. And that's it. There is our second expansion. Let's take a look at a couple more on the next slide. So here I have 2 more examples. We have example 3, with log base 4 of 64x squared. And I want to point out again here, I don't need any parentheses around this 64x squared because it's all one term. We only have to put parentheses around an argument if there's more than one term in the argument. All right, so I see two different bases here. I see a 64 and I see an x squared. They're being multiplied. There's a product of two different bases. So I will separate this out using the product rule. Pretty simple. We'll have log base 4 of 64 and log base 4 of x squared. Boom. Multiplication in the product or in the argument turns into addition as we expand. Okay, so we expanded that. Cool. And I want to point out something I said on the last slide. 64 and x squared are both in the numerator of a fraction. We normally do not write this over 1 here, so that's not really there. But they're both in the numerator, so both logs are positive logs. And again, we don't write that plus in front of the first log because it's just assumed to be positive. All right, so now we used the product and quotient rules, right? There is no quotient rule for us to use here, so we used the product and quotient rule, fine. What about the power rule? Let's see. Well, 64 doesn't have a power, but x does have a power. So what we will do is we will move that out front, and we will say we have 2 log base 4 of x. And log base 4 of 64 is still there. Finally, we have to check. You can see this base is numeric and this argument has a variable in it, so we won't be able to simplify this anymore. But we always have to check this base being numeric and this argument being numeric, can that log simplify? And in this case, yeah, again, we have a log that simplifies here. We have 3 plus 2 log base 4 of x. Moving on to example 4. You can see this one is getting a little more complicated, and I want to point out this is a natural log, ln, lowercase ln, and you can see here again we only have one term, so no need for parentheses, but in the numerator I can see I have 2 bases, and in the denominator I also have 2 bases, and for the sake of making this a little more fun, I'm going to make this e to the 5th power. So here we go with all of this. How can we separate this out? Ooh, that's a good question. Let's see here. When you have a square root covering, or any root covering more than one base, before you move on, I think it would be a good idea for you to separate the bases into their own square roots. So something like this. And yes, this is a 100% allowable thing to do. This was one of the exponent rules or exponent laws in a couple videos ago. Where if you have 2 bases being multiplied, like a times b, and they were both being raised to the same exponent, then you can distribute, more or less, distribute the exponent to each base. Now, we will talk about this x being an exponent here in a second. I want to expand this out using the sum and difference, or the product and quotient rule first. So here we will have natural log of x, natural log of y, natural log of z in a square root, and natural log of square root e to the 5th power. And again, we have two logs in the numerator, so each of those will be positive, two bases in the numerator, each of those will be positive logs, and two bases in the denominator, each of those will be negative logs. Now, maybe you've been watching my videos, you've probably heard me say in the past, half power is square root. Square root is a half power. So in addition to there not being any exponents, we also can't have any roots because z to square root of z is the same thing as z to the 1/2 power. E to the square root of e to the 5th is the same thing as e to the 5th to the 1/2 power. Alright, well, we don't have anything to do for natural log of x and natural log of y. There are no exponents on the x and the y, so we can say natural log of x plus natural log of y. The z natural log is pretty simple. We can bring this half power out front as 1/2. There we go, natural log z. But remember also the exponent law that said if you have a base being raised to a power, and it's being raised to another power, we can multiply these powers together. So 5 times 1/2 is 5 halves. So this is minus 5 halves natural log of e. Okay, so we did the product and quotient rule and expanded it out into multiple logs. We used the power rule to get the exponents to the front of the logs. Finally, we have to check. It turns out that natural logs have base e. And you might be saying, hey, well, this is a variable and this is a... No. E is a number. E, remember, is about 2.71. So we have a numeric base and we have a numeric argument where the rest of these are all variables. So what does that mean for us is that we have to ask what power of e will give you e to the 1st power. And it turns out that this is just 1. So 5 halves times 1 is just 5 halves. So we'll get a final answer of natural log of x plus natural log of y minus 1/2 natural log of z minus 5/2. All right, let's take a look at condensing. Condense into one logarithm. So these directions are how to condense logs, multiple logs. And most of the time you'll see directions that say something like condense the following or condense the logs into one logarithm, something like this. So it just depends on how your directions look. But normally the word condense is used, or combine these logs into one log, something like that. So the first thing we need to do is condense logs using the power rule. Then we need to condense logs using the product and quotient rules. Then we need to simplify if necessary. And again, most of the time, there will not be much simplification that needs to happen at the end. But you'll notice that from the expanding, these are in the opposite order. And that's normally because when you do something in the opposite order in math, you have to swap all of the steps around. So I think it makes sense mathematically and logically speaking. All right, so let's just jump right into some examples. We have example 1, log base 6 of 18 plus log base 6 of 12. All right, so the first thing we need to do is condense logs using the power rule. And when we use the power rule in condensing, we're looking for any numbers that are in front of the log, any coefficients for the log. And in this example, there are no coefficients for either of these logs. So we can jump down to step 2, which is condense logs using product and quotient rule. So in going backward, we need to condense these, remembering that positive logs will end up having their arguments in the numerator. Also, adding logs means to multiply. So I'll have log base 6 of 18 and 12, right? We're supposed to condense it down into one log, but the addition of these logs leads over into multiplication of their arguments. So now we have to do a little bit of simplifying. Of course, you can multiply 18 times 12. You'll get log base 6 of 216 when you multiply these together. And finally, you have to ask, is log base 6 of 216 some nice number? What power of 6 will give you 216? That's 3. 6 to the third power will give you 216. Cool. Next example, more numbers. These are all numbers here, right? We had a numeric base and numeric arguments for this first example, and we're going to do the same thing for the second example. No problem. So this time you can see that we have a subtraction here. And remember, when we were expanding, the only time that a log would get a negative sign is if this base was in the denominator. So that's something we got to keep in mind moving forward. First step, condense logs using power rule. We have coefficients this time for each log, so we need to move those to be the exponent. All right, so that means we will have log of 25 to the 1/2 power minus log of 8 to the 1/3 power. I want to condense these logs then using the product and quotient rules. So again, this log is positive. There's a positive sign in front of this log. Its argument will end up in the numerator of a fraction. So 25 to the 1/2. This log has a negative in front of it. So the argument of this log will end up in the denominator as we combine. And we still have the log of all of this. All right, last step, there is a little bit of simplification here again. We should find 25 to the 1/2 power. Remember, 1/2 power is square root. You can find the square root of 25 pretty simply. The square root of 25 is 5, and the 1/3 power represents a cube root. So 1/3 power represents a cube root, just like a 1/2 power represents a square root. All right, so the cube root of 8 is 2. And there you have it, example 2. All right, on this page, 3 more examples. This first one is a doozy. And I'm going to try to show you how to do this all in one step. We know that we will be combining all 4 of these logs into one log. So let's get it down here. We'll get a big old log base b. And I get questions from students, will there ever be logs that have different bases? Well, not in college algebra. If you see that you have a log base b and a log base 2, you cannot combine those together. Most college algebra professors and algebra 2 teachers want to see if your combining skills are up to snuff. So most of the time, I'm going to say 99.9% of the time, the bases will all match. All right. So we have 4 logs. Here's one. Here's another one. And here are the other 2. And I circled these in a very specific way. Because I want to do this all in one step, and I encourage you to also do this all in one step, any log that has a plus sign in front of it, like the 2 circled in red, those will end up going in the numerator of a fraction. And in fact, they're going to be multiplied. So this will be 15, that's the argument of the first log, multiplied by the argument of the second log. Sweet. Any log with a negative in front of it, highlighted by the yellow boxes here, will have their arguments be multiplied in the denominator of a fraction. So here we will have x, there it is, and here we will have x minus 2. Now, you may have noticed that I missed one super important thing here, and that is this 3. Hey, that log has a coefficient in front of it. It sure does. The coefficient will get moved over as an exponent on this x, like this. And there you have it. You've been able to do this log condensing in one step. So again, we take the argument of each log that's positive and we put it in the numerator multiplied together. We can take each argument in a log that's negative and put it in the denominator multiplied together. And then any coefficients become the exponents of those particular bases. So for example, if I had put a 6 here, then x squared minus 6x plus 8 would have a 6th exponent. All right. And there is some simplifying that can be done here, but I don't think it's necessary to show you that. Without the 6 here, it turns out you can factor this and cancel an x minus 2 in the top and the bottom. So there's your simplification for that. But most of the time when we are condensing, it'll look something like this. 2 log terms. There we go, there we go. And it really ends up being pretty simple. We have to combine these into one log base 4. And there will be this base times this base, all in the numerator of a fraction. We're done. There it is. The example 5 over here, something very similar. We will have a log base 7 of x plus 2, and that's because it's positive, so that'll be in the top, minus, so this will go in the bottom, 3 minus x. Cool. I hope that makes sense. Last couple slides will revolve around the change of base formula. The change of base formula is just a way to make sense of logs that don't. So for example, log base 3 of 7, I have no idea what that is. The best we can do right this very moment is that we can guess the exponent has to be between 1 and 2. Now, these are exponents, and more specifically, exponents of 3, because 3 is our base. All right, so if I raise 3 to the first power, and I raise 3 to the second power, that's 3 and 9. So the exponent I need to get to 7, which is between 3 and 9, the exponent has to be between 1 and 2. That's the only thing I know right now. Fortunately, we can figure out the exponent, or we can approximate or estimate the exponent, if we take the log of the argument over the log of the base. And what you'll notice, what I did here is both of these bases for the log are 10. So log of the argument divided by log of the base. If we do this, we can estimate the base to be 1.7712. And would you look at that? That exponent that we needed for 3 to give us a 7 is between 1 and 2. Cool. So the formula here is the log base b of m is equal to log of m over log of b. And what you can say for this is the base goes in the basement. So maybe that will help you remember where the base goes in this division. The next slide, we'll just take a look at a few examples, and that'll be it. Here we go. As promised, some examples. So we want to estimate these logs with wacky bases, and the reason this is happening is because of something you'll see regarding interest formulas very soon. So we'll get there when we get there. We can write this log here as log of 2 over log of 1.07. Yeah, decimals. Decimals are always fun. So if you take log of 2 and divide it by log of 1.07, you'll see that it'll be about 10.2448. And that's your answer. Again, you have to put the base in the basement. And what this is getting at, what this particular log is getting at, is something like if you got an account that pays 7% and you only get paid once a year, how long would it take for your account to double 2 times the original account? Well, it'd be about 10.2448 years, just over 10 years. So like that's where this is going. All right, let's take a look at example 2. I'm going to take this log and just split it up. You want to see something like log of 1.23 all over log of 1.0025. And you just type that into a calculator. And you get approximately 82.9091. And I should be using better notation. This is approximately 10.2448. All right, let's take a look at example 3. From here, you can see that it's changed a little bit. We have a need for a change of base formula, and whatever we get, we need to divide that by 2. So let's first just work with this top part, which would be log of 5 over log of 1.09. And again, you can just plink that right into a calculator, and you get 18.6758. And from there, you cannot forget about this divide by 2. So we would have to divide this by 2 and get something like 9.3379, something like that. All right, last example, similar idea. Here we have this wacky log base something, log base 3 of 196. And we have to figure out this change of base. And then once we figure that out, we can subtract 7 from it and then divide it by 14. So let's figure out this part first, which would be log of 196 all over log of 3, which is going to be approximately 4.8043. Then this is what goes in the red circle here. So we can take 4.8043 and we can even write it down like this, minus 7 over 14. So we have to take away 7 from the numerator and then divide it by 14, and you'll get something that is approximately 0.0575. And again, this is going to end up looking like some sort of rate for us when we start looking at more complex compounded interest examples. That's it. This video is over. I hope you understand a little bit more about expanding condensing logs and the change of base formula. Good luck.